Okay, today's video is over rectangular tangent lines, or essentially tangent lines that can be represented on a Cartesian plane or rectangular plane. Now, that type of plane being one where every coordinate can be represented by 2 points, typically with x and y, and each curve can be represented with one equation. So that's what a rectangular plane is. I thought I should mention. Okay, so tangent lines are very applicable and seen in both calculus AB and BC. However, in BC, polar tangent lines and parametric tangent lines are more so common. Today, we're just going to go over rectangular, but I suppose I should actually tell you what a tangent line is. It's just the representation of a slope at a certain point. Now, try to recall that a tangent line only hits a slope or only hits a function at one point, and that's why it's such a great representation. Because if we were to have a some sort of function like this, a parabola, well, we can represent the slope of this function, the slope of this point here on the function, as just a line that hits it once. And they will both have the same slope, at least at that point. And so today we're going to go over how to find the tangent line. What you'll need is an equation that's differentiable, as well as 1 point. And from there, you can find the tangent line. And you're going to want to represent a tangent line in the standard form y minus a equals m x minus b. Now, a and b will be the coordinate at which we're trying to find the slope of a function. We're trying to find the tangent line to a function. And m is just the function differentiated at a. So that's all you need for a tangent line. And I'll go over a few examples showing exactly what you should do. Okay, so this is the function that we're going to try to find the tangent line of at point x equals pi. So the first thing we're going to do is we're going to try to find the derivative of the function, which we'll represent as f prime of x. Now, to find the derivative of our function over here, we're going to have to employ the product rule, I believe is what it's called. Meaning we're going to have to write the first term and the derivative of the second, which in this case is going to be 2 cosine 2x, plus the second term times the derivative of the first, which will be e to the power of x. And so this is what we have so far. This is the derivative of f of x. And all we have to do is find the derivative at point pi. So we're at point x equals pi. So we'll just plug in everything. Over here, we end up with 2 times e to the power of x. Now, cosine 2 pi over here, if we were to replace x with pi, is equal to 1. You'll know this if you've memorized your unit circle. Even if you haven't, you may already know it. Now, if we were to plug the pi in over here for x, we'd end up with a 0 because sine of 2 pi, sine of pi, sine of 0 is always 0. And 0 times f of x is 0 as well. So we end up with 2 times e to the power of x plus 0, which is just 2 times e to the power of x. Sorry, for some reason I did not replace x with pi. So our final answer for the derivative of f prime of pi is 2 times e to the power of pi. So if I were to write the template of the standard formula, we'd end up with y minus a equals m x minus b. Now we have b, it's pi. We have m, it's 2 times e to the power of pi. We just need to find a, which is the y coordinate at point x equals pi. So we'll plug that into our equation. We'll say that f of pi is equal to e to the power of pi times sine of 2 pi. Now, as I said earlier, sine 2 pi is 0. That's 0, so we end up with e to the power of pi times 0, which is 0. So we have our point. It's x equals pi, y equals 0, and we have our slope. So we can fill in our standard equation, or our tangent line, I suppose, by y equals 2 times e to the power of pi times x minus a, or x minus b, which in this case is going to be pi. And this right here is our tangent line. It's pretty simple. It's also, I forgot to mention, a way to approximate the value of a curve, as I'll show you in this next example. Okay, this is practice problem 2. We're told to approximate the value of f 3.1 if f of x is equal to natural log 4 minus x plus x squared. Now, usually or always, AP exams will tell you the method of which you should approximate a function. In this case, we're going to use tangent lines. Now, I'll show you why tangent lines are an inferior method of approximating compared to other methods. And that's because it's never accurate. If we were to give, or if it would only be accurate if we were approximating a linear function, but very rarely would you do that, if not ever. So let's say you have a parabola, and let's say that this point right here, let's call it x equals 3, is represented by red, and this is x equals 3.1. So if I were to find the tangent line of 3, it is never going to be equal to 3.1, and that's because it only touches the curve once. So it will never touch 3.1 because it's already touching 3, if that makes sense. And so, although the difference may be minor, it still exists. So it's still used as a method of approximating a function, but it certainly isn't consistent because the error changes depending on like the severity of a curve of a function. So, but it is featured on the AP exam, and so we're going to go over it. First things we're going to do is find the derivative of f of x, which is going to be the derivative of natural log 4 minus x plus the derivative of x squared. So the derivative of 4 minus x, of natural log 4 minus x, is negative 1 over 4 minus x. If you're confused as to how I managed to find the derivative of this term, or the end product, I've made a video on the past, in case you're curious. And from here, we have to find the derivative of the second function, which is going to be 2x. So we'll have to find, from now, the derivative. Oh God, I forgot that in the question I never actually specified at which point we should find the tangent line. Let's say x equals 3. So we're going to find the derivative of f of x at point 3. So we're just going to plug in 3. We end up with negative 1 over 4 minus 3 plus 2 times 3, and we'll simplify. We end up with negative 1 plus 6, which is equal to 5. So the derivative at the slope of the function at point 3 is 5. Now we already have the x term. In this case, it's going to be 3. From here, we just have to find the y term. So we're going to find f of 3, which is equal to natural log 4 minus 3 plus 3 squared. Now, 4 minus 3 is 1. So this term over here could be represented as natural log of 1, but that's equal to 0. So we're going to just omit that term. And 3 squared is just 9. So we end up with 0 plus 9, which is 0. So our point is 3, 9. Sorry, I don't know why I said this is equal to 0. It's obviously 0 plus 9 is 9. So our coordinate can be represented as 3, 9. Now, the template for the standard equation is y minus a equals m, x minus b, where b and a are x and y respectively. So from here, we can just plug in our values. Y minus 9 is equal to 5, x minus 3. And that is the tangent line representation of f of x being natural log 4 minus x plus x squared. But we're not yet done. We have to find f 3.1. So let me just erase a few things to make room for the next section. And it's actually incredibly easy. What we're going to do is we're going to just plug in 3.1 for x. So we end up with, I'll show it up here. Y minus 9 is equal to 5, x minus 3. However, we're going to replace x with 3.1. Now 3.1 minus 3 is 0.1. And so what we really end up with is y minus 9 is equal to 0.5. We can, of course, add 9 to both sides, and we end up with y is equal to 9.5. And that is the final approximation of f of 3.1. And that's it for today's video. If you have any suggestions for future videos, please put them in the comments. Thank you.